Not a planet rumor, not Nibiru, not a gap in the data waiting for a better telescope to fill. A gravitational signal from something with no confirmed identity, measured with enough precision to be statistically undeniable, that three separate physical explanations all predict, and none can currently be ruled out. A telescope built to see the first galaxies after the Big Bang is producing its most immediately disruptive science not at 13 billion light-years, but at 50 astronomical units in the outer edge of our own solar system, because its infrared sensitivity is precise enough to measure orbital trajectories that no prior instrument could pin down to the accuracy the anomaly requires. The gravitational signal Webb is measuring in the outer solar system is real. It does not match what the known mass of the solar system predicts, and the three explanations that fit the data, an undetected planet, a population of primordial black holes, or a dark matter substructure gravitationally bound to the solar system, are currently indistinguishable from each other by any instrument that exists, which means the anomaly is not a mystery waiting to be named, but a test of physics that we are only now precise enough to run. What makes this impossible to resolve quickly is not a gap in ambition or a shortage of telescope time. It is a specific property of how gravity works at the distances involved. Beyond 50 astronomical units from the Sun, beyond a distance where light takes 7 hours to travel one way, the gravitational acceleration experienced by any object falls to values so small that the difference in gravitational pull between a single large planet, a cluster of primordial black holes adding up to the same mass, and a diffuse concentration of dark matter producing the same total gravitational influence is invisible in the orbital trajectory data at any precision currently achievable. All three produce the same orbital clustering signature. All three pull Kuiper belt objects into the same statistical alignment. The orbital mechanics cannot distinguish between a point source and a distributed source when the measurement precision is lower than the difference between their signatures. And right now, even with Webb, we are at the edge of where the signatures begin to diverge. The question the anomaly poses is not what is out there. It is which of three physically distinct things is out there. And the answer requires either more orbital measurements, a different kind of observation entirely, or an instrument that does not yet exist. The Planet 9 hypothesis is the most familiar of the three explanations, and it deserves its place in the conversation, not because it is certainly correct, but because it was the first rigorously formalized explanation for the orbital clustering, and the framework it introduced for measuring the anomaly's statistical significance is the same framework Webb's measurements are now being applied to at higher precision. In 2016, Konstantin Batygin and Mike Brown at Caltech analyzed the orbital parameters of 6 trans-Neptunian objects orbiting the Sun beyond Neptune, and found that the probability of their orbital clustering being random was roughly 0.007%. That is a very low probability of coincidence. The most natural explanation for a non-random clustering of orbital planes is a gravitational body pulling them into alignment. Batygin and Brown estimated the perturbing body would need to be roughly 5 to 10 times Earth's mass in a highly eccentric orbit, taking it to distances between 400 and 800 astronomical units from the Sun, far enough that it completes one orbit every 10,000 to 20,000 years, which is why it might plausibly have escaped detection. The planet hypothesis has a decade of dedicated deep infrared surveys behind it. Multiple deep infrared surveys have covered significant fractions of the sky at the distances Planet 9's orbit would place it. None have found it. This is not a conclusive refutation. The sky is large, the predicted location is uncertain, and a planet at 800 astronomical units reflects very little sunlight. But the null detection result has shifted the distribution of scientific opinion. A growing fraction of the astrophysics community has moved from treating the search failure as a temporary coverage gap to treating it as evidence that the orbital clustering has a different physical cause. The question that follows is what that cause is, and the alternatives the data is consistent with are not simpler than a planet. Primordial black holes are a consequence of the physics of the very early universe. In the first fractions of a second after the Big Bang, density fluctuations in the plasma that filled space could, in regions where the fluctuation was large enough, collapse directly into black holes before any star or galaxy formed. These primordial black holes are not the stellar mass black holes produced when massive stars die. They can be far smaller, ranging from asteroid mass to many times Earth's mass, and they produce no light, no heat, and no electromagnetic signal of any kind. They are detectable only by their gravitational influence on nearby objects or by the rare chance alignment that produces gravitational microlensing, the brief brightening of a background star as the black hole's gravity bends and focuses the star's light. A population of primordial black holes distributed through the outer solar system, adding up in total to the same 5 to 10 Earth's masses that Planet 9 requires, would produce gravitational perturbations on Kuiper belt objects that are statistically identical to the perturbations a single planet produces. The orbital clustering would look exactly the same. The infrared surveys would return exactly the same null result they currently return for Planet 9, because there is nothing to detect in infrared. A population of objects with no surface temperature does not emit thermal radiation. Dark matter substructure is the third candidate, and it is the one that astrophysicists discuss with the most careful hedging because the implications extend furthest if it is confirmed. Dark matter, whatever it is not uniformly distributed through space. Simulations of large-scale structure formation predict that dark matter organizes into filaments, halos, and substructure clumps at every scale, down to clumps potentially small enough to be gravitationally bound to individual solar systems. If a dark matter substructure clump is gravitationally associated with the solar system, not passing through, but orbiting within it, concentrated in the outer solar system region where the Kuiper belt anomaly is observed, its gravitational influence on trans-Neptunian objects would be distributed rather than point source. The orbital clustering it produces would be subtly different in character from the clustering a single massive body produces, but at current measurement precision, not different enough to distinguish. Unlike Planet 9 and unlike a primordial black hole population, a dark matter substructure clump cannot be detected by any electromagnetic observation at all. It does not interact with light by definition. The only way to measure it is through its gravitational signature, which is exactly what Webb is now measuring with enough precision to potentially begin separating from the other two explanations. Webb's contribution to this investigation is precision, not serendipity. When the telescope resolves the position and proper motion of a small Kuiper belt object at 50 astronomical units, it is measuring an object moving at roughly 3 to 4 kilometers per second against a background of distant stars at a resolution sufficient to detect deviations in its trajectory of a few millimeters per second over the observing baseline. Those deviations accumulate over years of repeated observation into orbital parameters precise enough to test whether the object's trajectory matches what Newtonian gravity plus the known solar system mass predicts, or whether there is a residual pull whose direction, magnitude, and consistency across multiple objects reveals the source's nature. Before Webb, the precision flaw was higher than the anomaly's signal. The clustering was visible statistically, but the individual orbital residuals were too uncertain to contribute to distinguishing between explanations. Webb pushed the measurement precision below the noise floor of the anomaly and above the noise floor of the differences between what a planet, a primordial black hole population, and a dark matter substructure each predict for individual object trajectories. The measurement that would most cleanly distinguish between the three explanations is not an orbital measurement at all. It is a microlensing survey. A primordial black hole moving through the outer solar system on an orbital trajectory would, during the fraction of its orbit where it crosses the line of sight to distant background stars, briefly focus that starlight into a brightening event with a characteristic duration and magnification pattern that depends on the black hole's mass. A survey sensitive enough to detect these events across the relevant volume of the outer solar system would either find a population of lensing events consistent with the primordial black hole hypothesis or return a null result that statistically rules it out. The Rubin Observatory's legacy survey of space and time, which began full operations in 2025, has the cadence and sky coverage to detect microlensing events in the outer solar system at the mass range Planet 9 requires, and its data stream is specifically being analyzed for signatures consistent with dark objects rather than luminous ones. This is the dataset that astrophysicists working on the Kuiper belt anomaly are watching most carefully. The Voyager probes are the only human-made objects in the relevant distance range. As of early 2026, Voyager 1 is beyond 172 astronomical units from the Sun, already traveling through interstellar space, on course to reach one full light day from Earth by November 2026. Voyager 2 is past 142 astronomical units. New Horizons, which flew past Pluto in 2015, is now beyond 60 astronomical units and heading outward. All three are tracked by the Deep Space Network with enough precision to detect trajectory deviations from predicted paths, the same technique that revealed the Pioneer anomaly in the 1990s, a small unexplained acceleration in the Pioneer 10 and 11 probes that was later explained as anisotropic thermal radiation from their own electronics. A gravitational perturber of 5 to 10 Earth masses at 400 to 800 astronomical units would produce trajectory deviations in the Voyager and New Horizons probes that, accumulated over years of tracking, would be detectable against the background of known gravitational influences. The current tracking data constrains the mass and location of any perturbing body at certain distances, but does not yet rule out all orbital configurations consistent with the Kuiper belt clustering. The constraint gets tighter every year the probes are tracked, not because the probes accelerate their data collection, but because more years of trajectory data means smaller error bars on the accumulated deviation. The irony embedded in this investigation is specific. Webb was designed around science goals that were required it to be pointed at objects 12 to 13 billion light-years away, at the edge of the observable universe, to capture photons that have been traveling since 380 million years after the Big Bang. The telescope's infrared sensitivity, mirror area, and positional stability were all optimized for that purpose. The secondary yield of that optimization, the ability to measure the orbital mechanics of objects 50 astronomical units away with millimeters per second velocity precision, was not the design target. It was a consequence. The instrument that humanity spent 30 years and $10 billion building to see the beginning of the cosmos is currently producing scientifically disruptive results about something hiding in the nearest dark region beyond the last known planet, because the precision required to see the edge of the universe turned out to be more enough precision to see something much closer that nobody could previously measure. The statistical significance of orbital clustering has improved substantially as Webb's measurements have been incorporated into the trans-Neptunian Object Orbital Catalog. The original 2016 dataset of 6 objects with anomalous clustering has grown. The growth has not uniformly strengthened the signal. Some newly measured objects fit the clustering pattern, some do not, and accounting for observational biases that make certain orbital configurations easier to detect than others has reduced the statistical significance below the original estimate. The community's honest assessment is that the anomaly is real. Its statistical significance is meaningful but not overwhelming at current sample sizes, and the next 5 years of Webb observation time dedicated to the Kuiper belt object orbital mapping will produce a dataset large enough to either confirm the anomaly at high significance or reveal it as an artifact of the observational biases that earlier, less precise measurements could not fully characterize. That 5-year window is the most scientifically consequential period in outer solar system research since Voyager 2 flew past Neptune in 1989. At the end of it, one of 3 outcomes applies. The orbital data converges on a point source signature consistent with a single large body, strengthening the Planet 9 interpretation and motivating a targeted direct detection campaign. The orbital data converges on a distributed source signature, inconsistent with a point mass, ruling out a single planet and pointing toward either a primordial black hole population or dark matter substructure. Or the data remains ambiguous, with sample size insufficient to distinguish between the explanations even at Webb precision, requiring a dedicated outer solar system mapping mission that no space agency has currently funded. Each of these outcomes tells us something different about what is in the outer solar system. 2 of them, the distributed source result, would be among the most significant astrophysical discoveries in modern history, not because they reveal an object, but because they reveal a class of physics that has never been directly detected at solar system scales. The Kuiper belt is 30 to 50 astronomical units from the Sun. The objects in it are small, dark, cold, and moving slowly enough that measuring their orbital parameters requires years of repeated observation at high positional precision. None of those properties make them seem like the frontier of fundamental physics. They are, anyway, because the gravitational acceleration at those distances is low enough that dark matter concentrations, primordial relics of the early universe, and modifications to known gravitational theory all leave distinguishable fingerprints in the orbital data if the measurement precision is high enough. Webb pushed the precision high enough. What it found is a signal that does not have a confirmed source. Whether that source turns out to be a cold, dark planet, a cluster of invisible primordial remnants, or a shadow of dark matter clinging to the edge of the solar system, the physics that answers the question will not leave the standard model of the solar system unchanged. The only remaining question is which version of unchanged it will not be.